Hello, everyone. Thank you for tuning in. My name is Ben Moulton. I'm a PhD student at Utah State University, working with Doug Hunsaker. So this presentation that I have here is on some work we did at looking at the aircraft equations of motion, deriving the handling qualities from those, but looking at them in an alternate method. So this presentation is has to do with a paper that I presented at the AIAA SciTech 2023 forum, and for more information, I'll have a link in the details that'll go over that. But just getting started, when we talk about non-dimensionalizing some parameter, we're just talking about getting rid of the units. So a lot of you will be familiar with something like a percent error. So what we'll do is we'll take the difference between truth and whatever our approximate value is, and we'll divide by truth, and that's what we use to determine, this percent error. And something that some other people will be familiar with is a Mach number. Now, a Mach number is where we take a velocity and divide it by the free stream speed of sound velocity to get this dimensionless ratio. In other words, getting rid of the units. When I say dimensionless, that's what I mean. And the last thing is a lift coefficient. So in aerodynamics, when we non-dimensionalize the lift, the body lift force, we not divide it by the dynamic pressure multiplied by the main wing area, and that's just because those are appropriate units. They have to do with aerodynamics, and so what I want to stress here is we always use something that's appropriate. Um, and so a method that we will frequently use to do these non-dimensionalizations is called Buckingham's Pie Theorem. Now, Buckingham's Pie Theorem states that if we have an equation of n terms and k dimensions, so mass, length, time, um, if we have an equation of n terms with these dimensions, then we would be able to reorganize this equation into p terms where p is equal to n minus k. And so what we wanted to do was look at non-dimensionalizing these equations of motion in a slightly different method. What we could we learn? What are the benefits? Um, and so just starting off the equations of motion, there's 12 equations of motion. The first half of these equations of motion come from Newton's second law. So you can see on the top we have a sum of forces, and just below that we have a sum of moments on our rigid body aircraft. And then our second set of equations, or our second two sets, excuse me, of equations have to do with the kinematic translation and rotation velocities. So the first of those sets of equations has to do with translating the body fixed velocity into the earth fixed velocity. And on the bottom we have the body fixed rotation rate multiplied by some rotation matrix into the earth fixed rotation rate. So these are the equations of motion that we get when we use those when we plug in our rigid body aircraft. And so at the top we've got a change in our body fixed velocity. The second set of three equations, we have a change in our body fixed rotation rate. The third set of equations, we have a change in our earth fixed velocity. And the last set of equations is a change in our earth fixed orientation. Um, excuse me, that third set of equations is a change in our Earth fixed position. But so now that we have all this information, the first thing that we will do is we will non-dimensionalize this system of equations. But before we do that, we're going to linearize this system. So what do I mean by linearized? When we linearize a system of equations, we use something called small disturbance theory. And so basically what we're looking at is for some disturbance from some nominal position. So here we'll use a first order Taylor series expansion, and we'll neglect higher order terms. And so just as a reference, the reference condition that we're doing this about is steady climbing flight. So once we linearize these systems of equations, we actually are able to make some assumptions about the aircraft, and we're able to split it off into a longitudinal set of equations and a lateral set of equations. So you can see here the linearized longitudinal equations of motion. And then here we have the linearized lateral equations of motion. Um, and then what we would do traditionally is we would non-dimensionalize these using traditionally aerodynamic parameters. So for example, here we have the traditional linearized dimensionless longitudinal equations of motion, and I apologize, that's quite a mouthful. And then over here we have the traditional linearized dimensionless lateral equations of motion. You'll notice a lot of these c variables. More often, generally those are non-dimensionalized using like that dynamic pressure and wing area, and then usually there's a reference length somewhere in there. Now, those work great for aerodynamics, but what we wanted to look at was, they're not terribly appropriate for looking at the dynamics of some aircraft, where we're not so much concerned about the dynamic pressure, but we're more concerned about velocity, gravity, weight, and components of inertia. And so we took a look at using Buckingham's Pie Theorem. And now, once again, we have these equations of n terms, and we had a system of equations of forces and moments, and one of velocities, and a set of equations of the rotation rates. And so we were able to figure out some set of k dynamics-based variables, once again in terms of dynamics-based variables instead of aerodynamics-based variables. And so we're able to define these p dimensionless coefficients, and there's an example there of we have some derivative, it's a capital K, and then in the subscript we have a function, comma, and the argument of the derivative. So here we have some examples of these alternate coefficients. Once again, we could spend a lot of time talking about these, but for more information I direct you to the paper. That gives quite a bit more detail about the derivation as well as the development of these equations. So at the top left, we have a kf variable. That's how we would non-dimensionalize a force. So you'll notice once again, whereas before we talked about the lift coefficient divided by the dynamic pressure in the wing area, now we're just dividing by the force, which is more appropriate once again for the dynamic conditions that we're looking at here. And then in the top right, we have a moment coefficient. And so instead of dividing by some dynamic pressure and wing area and some reference length, we'll multiply it by velocity squared and divide by gravity squared and divide it also by some reference inertia, depending on the moment axis. So for example, if it were a pitching moment, coefficient there, we'd use the IYY moment of inertia. And then on the middle row, we have our dynamic rates. So you'll notice usually, for those of you who are familiar with the way we non-dimensionalize body fixed rotation rates in aircraft dynamics, we usually use something like reference length, which is usually CW bar divided by 2 or BW divided by 2. And then we'll use velocity and that's it. But when we're doing this based on dynamics dynamics, it actually kind of falls out this way that we use velocity and gravity. And we're not the first ones to notice this. This was actually something that was noticed by Phillips in his book Mechanics of Flight. He goes into a little bit of detail as to why the pitching rate should be non-dimensionalized this way, and he calls it a dynamic pitching rate, and that's the methodology that we follow. We call these dynamic rates. And he talks about how that can be related to the NZ acceleration component on an aircraft. And once again, for more information, I direct you to the paper as well as to the work by Phillips. The last benefit, the last thing I wanted to focus on with these alternate coefficients is this time variable on the bottom. So whereas in our traditional formulation that we talked about a little bit earlier, we would get time based on the linearized lateral equations of motion and a time based on the linearized longitudinal equations of motion, we'd get these two different time non-dimensional time variables. We actually get a single non-dimensional time variable, even though our system is uncoupled between longitudinal and lateral. And that's amazing. So just to kind of give you an idea, that means that whereas in the traditional sense, when we had non-dimensional eigenvalues of our system, we wouldn't be able to compare them because they wouldn't have the same non-dimensional unit. They wouldn't have the same dimensionless time variable. But in our system, we have a new dimensionless time variable that is the same across linearized and longitudinal systems, longitudinal and lateral systems. And that means that we can compare these eigenvalues before we even redimensionalize them. And that's crazy. And so the last thing I wanted to do, I guess before I get into that, I wanted to show these alternate linearized equations of motion. So here's the alternate linearized dimensionless longitudinal equations of motion. And here's the alternate linearized dimensionless lateral equations of motion. And you'll notice that we have all these k parameters rather than the capital C parameters. And so if we use a similar process presented by Phillips, we can develop closed form dynamic mode approximations for each of these dynamic modes of this aircraft. So on the top we have an eigenvalue for the short period mode, and then we have an eigenvalue of the phugoid mode, the eigenvalue of the roll mode, and the eigenvalue of the spiral mode, and then the eigenvalue of the Dutch roll mode. And once again, for more information on these, I direct you to look to the paper. So, just kind of wrapping things up, why the heck do we care? These new dimensionless ratios give a better physical sense of the system. So, for example, moment rotations are related to an inertia rather than some dynamic pressure and reference area and reference length. Once again, we have these dynamic rates that are related to the velocity and gravity of the aircraft, gravitational force on the aircraft, or excuse me, um, rather than the velocity and some arbitrary reference length. And the last thing, once again, is that dimensionless time variable we talked about. That was the same across these linearized longitudinal and lateral systems. And once again, looking at these eigenvalues, we would be able to compare non-dimensional eigenvalues, between the longitudinal and lateral modes, where we wouldn't be able to do that with the traditional method. So some further work, we would love to look at some of the implications of this method. How do the dynamic scale of these non-dimensional eigenvalues compared to the traditional method, as well as running these results on aircraft, and then also looking at, and this is just kind of a sneak peek at some things we've noticed, looking at what if we redimensionalize these eigenvalues now that we've gone through this whole system and have these dynamic mode approximations. What if we redimensionalize them and looked for certain parameters, say, for example, a static margin, or something that Phillips has presented called the dynamic margin, and they do show up. So Phillips actually noticed that the short period cap, so the control anticipation parameter, that is almost directly related to the dynamic margin of an aircraft, with a couple things involved there. But and so we feel like there has to be something like that inside these equations. And so we've been noticing, especially for the short period mode and the phugoid mode, the static margin and the dynamic margin. Once again, for more information, that I direct you to Phillips. These things show up in the equations everywhere. And what we're looking for, and what we expect to see somewhere in, for example, the Dutch roll mode eigenvalue, is to see something similar but related more to the roll and yaw axes. And once again, we've noticed some things, but that will be in future work. So, alrighty, okay. Thank you so much for listening, and I look forward to having any questions or comments, answering any questions or comments you may have. And once again, this was presented in the SciTech 2023 forum. Thank you.